Hi there, this is Jenna Nichols. We're going to talk about structure 1.3.6 today. This is higher level only, and it's about ionization energy and how that's related to convergence limits. So let's define ionization energy really quick. I'm going to use a Bohr model for this, even though we know now that it's not the most accurate. But it's still useful sometimes to use some of these older models just as illustrations. So let's say we've got an atom of aluminum. Aluminum has 13 electrons. So I'm going to use the Bohr model here. 13 electrons. So it has 3 valence electrons. The protons in the nucleus are exerting a force of attraction on all of those electrons. Now, the force on the closest electrons is larger than on the electrons in the second energy level, and the least amount of attractions are towards these electrons in the outermost energy level. So the closer it is to the nucleus, the more the electrons are being attracted to the nucleus. Now, if you add energy to the atom, the electrons can move between energy levels. We talked about that as atomic emission. So if you add energy, the electrons can jump one or more energy levels, and then they will relax back down to by releasing those photons to get back to their ground state. But if you add enough energy, the electrons can actually leave. And so ionization energy is defined as the amount of energy it takes to remove the electron from the atom. Now it's going to be different depending on which electron you're talking about. So the first valence electron to be removed, let's say it's this one, that will be called the first ionization energy. Oops. And that will always require the least amount of energy to remove the first electron. It's going to require just a little bit more energy to remove the second electron, and then a little bit more energy to remove the third electron, just based off of a difference in charge ratio, right? Protons per electron. If you were to then look at the fourth electron to be removed, that would have to remove from a core electron. That's the third, that would be the fourth. So much closer to the nucleus. It would take significantly more energy to remove the fourth electron from an aluminum atom. So you can kind of start to see how we're going to need to look at protons in the nucleus, the total number of electrons, and the number of energy levels when we're looking at ionization energy, and whether we're looking at first, second, third, fourth, etc. ionization energy. Also, this is a good time to mention that when we're removing the electron, you're breaking a force of attraction between the proton and the electron. And anytime you are breaking a bond or breaking a force of attraction, that requires an input of energy. So this is going to be endothermic, which is why all of our ionization energy values are going to be positive values, because it requires an input of energy to break that force. Ionization energy is also really closely related to something we call metallic character. So I'm going to look at a couple elements to kind of describe this. So let's start with lithium and beryllium. I'm going to use Bohr models again because they're easy to draw and to show what I mean. So lithium has 3 electrons and beryllium has 4 electrons. Lithium also has 3 protons and beryllium has 4 protons. So because beryllium has more protons, it's going to exert more force on its valence shell than lithium, considering they have the same number of energy levels. So this is n equals 2, n equals 2. So the first ionization energy, you'll be removing this outermost electron for either of them. It's going to require more energy to remove the beryllium electron because it has more protons. So more positive charge, greater force of attraction. Lithium is easier to remove its valence electron, so it has a lower ionization energy, and that means it has a more metallic character. character I can spell. Now, so that's really important to notice. The lower the ionization energy, the more metallic the element behaves. Metals want to lose their electrons. And the easier it can lose the electrons, the more it can behave as a metal, as a positively charged ion. It can conduct electricity better if the electrons are more free to move. It can form ionic compounds with nonmetals easier. So lower ionization energy makes it more metallic. Let's look at another comparison. I'll do a quick lithium drawing, again, just as a comparison. And I want to compare that to sodium. Now, sodium has 11 electrons. It's in the same group as lithium. So it has 1 valence electron, just like lithium. Now, lithium has 3 protons and sodium has 11 protons. But even though sodium has many more protons, the valence electron is much further away from the nucleus. And in fact, some of that charge is being blocked by these core electrons. So sodium has a lower ionization energy than lithium. Ionization energy. Lithium is going to be harder to remove its electron because it's much closer to the nucleus. Sodium, it will be easier because the valence electron is further away from the nucleus. And that goes back to the forces of attraction. We call those Coulombic attractions. They're based off of distance and the size of the charge. In this case, the distance from the nucleus to the electrons is a greater factor there. So sodium is going to behave more metallic, have more metallic character than lithium because it has that lower ionization energy. Okay, so we kind of talked about the pattern already, but let's look at kind of a generic periodic table here. So we just talked about lithium, beryllium, and sodium. And so as you go across the periodic table, in general, the ionization energy increases because you have more protons in the nucleus, so greater force of attraction. As you go down a group, in general, your ionization energy will decrease. And that's because you have more energy levels. The valence electrons are further from the nucleus, so you will have a lower amount of ionization energy, easier to remove an electron. Now, I will say that a good thing to notice here too, because we haven't really talked about it yet, is that the trends become what we call periodic. So as you increase an atomic number, like if I go from lithium all the way to neon, the ionization energy will increase. So again, in general, it will increase until you get to neon, and then suddenly it will jump down because we said sodium has a lower ionization energy than lithium. So it will be lower, and then that will gradually increase until it gets to the end of the row, argon, and then it will jump back down again. So it has this repetition of increase, decrease, increase, decrease as you go across a periodic table. And that was one of the ways that they were actually able to develop the periodic table to begin with, by looking at trends in physical and chemical properties that repeated as you got to heavier and heavier elements. And elements that are in the same group will have similar chemical properties, and you'll be able to predict patterns in other properties like ionization energy. Now this isn't exact, and we're going to look at a few exceptions, but this is kind of like the general idea. So the first exception that we want to look at is the difference in ionization energy between groups 2 and 3. So let's do really quick. We'll do beryllium and boron. Beryllium's in group 2. Beryllium has 4 electrons. Oops, weird box. So 1s2, 2s2. Boron has 5 electrons. So 1s2, 2s2, and then 2p, 1. So, and remember, beryllium has 4 protons, boron has 5 protons. So you would expect boron to have a higher ionization energy because of the additional proton. However, the difference, remember this is group 2 and this is group 3, is because of this extra electron is now in a different sublevel. So because of that difference between the S and the P sublevel, it winds up being slightly easier for boron to lose that first electron than it is for beryllium to lose its first electron. And again, we're comparing the first electron to be removed. And so that occurs for whenever you're comparing group 2 to group 3 in the same period. The group 3 will have a very slightly lower ionization energy compared to group 2. You see a similar kind of breaking of the pattern between groups 15 and 16. So let's look at, actually I'm going to draw all of them, carbon, nitrogen, and oxygen. So carbon, this is 1s, 2s, and then 2p for all of these. Just label it once. Carbon has 6 total electrons. So it looks like this. Nitrogen has 7. Oxygen has 8. And carbon has 6 protons, nitrogen has 7 protons, oxygen has 8 protons. So if you were following the normal trend, you would expect carbon to have the lowest first ionization energy and oxygen to have the highest first ionization energy. Carbon is the lowest in this case to remove its first electron. But if we're looking at the difference between nitrogen, which is in group 15, compared to oxygen, which is in group 16, you're removing this last electron in nitrogen compared to this electron being removed in oxygen. And it's always the last one you would add as you're making an orbital diagram. And it winds up that removing this second electron in one of those p orbitals is just a little bit easier to remove because of the extra electron-electron repulsions. So the fact that they're the same charge, they repel each other. So electron-electron repulsions actually make it a little bit easier to remove that first electron from oxygen compared to the first electron from nitrogen. So you see a breaking of the trend between groups 15 and 16 because of that. I would say whenever you're in doubt for these patterns in first ionization energy, it's worth your time to draw the orbital diagram to see if that will help you explain why there's a difference in the trend. Let's review convergence really quick. So if you remember when we talked about hydrogen, the difference in energy between the first and second energy level, the second and third energy level, the third and fourth energy level, you'll see like there's a decreasing difference between them. And I tried to show this, but it's kind of hard on the tablet. So you see there's a smaller and smaller difference. That's called convergence. Eventually it will reach a point where the difference between the energy levels is so small that the electrons can effectively just move between them, and that effectively means that the electron has left. And so we call that the convergence limit, where it's basically when it gets to a high enough energy, the difference between energy levels is so small, and it makes it effectively that you're losing the electron at that point. And it is different for different elements, of course, because of their protons and the different energy levels. And so it's going to be very different for different things. Okay, let's quickly review energy, frequency, and wavelength. Energy is typically measured in joules. Frequency, you'll see V or F for frequency, and you typically measured in inverse seconds. Let me rewrite that so you can see it. And then wavelength, which is typically measured in meters. Sometimes you'll see nanometers. And the relationship there is as you have a higher energy, higher frequency as well, but a shorter wavelength. So wavelength is inversely proportional to the other two. Now we can actually relate these to each other quantitatively using two equations. And these equations are in your data booklet. And it's E equals HF. And the other equation is C equals lambda F. And E, of course, is energy in joules, frequency in inverse seconds in both equations, wavelength in meters. H and C are constants. H is called Planck's constant, and it is 6.63 times 10 to the negative 34. And the value for C is the speed of light, which is 3 times 10 to the 8th meters per second. So you can convert between energy, frequency, and wavelength using these two equations in the data booklet, and they give you the constants as well. Okay, so if we put all of that information from earlier together, you know about ionization energy, you know about convergence limits, and we know the equations that relate energy, frequency, and wavelength. So we can measure the wavelength of the convergence limit for an atom. For hydrogen, for example, is 9.12 times 10 to the negative 8th meters, which is in 912 angstroms. We need it in meters, though. We can actually use that wavelength to then calculate the frequency and therefore the energy of a single photon at this wavelength, which is the amount of energy it would need to effectively remove that outermost or that electron from the hydrogen atom. There's only one electron. So let's do that. We're going to start with the wavelength equation, C equals lambda V, or lambda F for frequency. So we're going to plug in the speed of light, that wavelength in meters, and solve for F. And so you'll divide both sides by that wavelength, and you get that the frequency to 3 sig figs is 3.29 times 10 to the 15th inverse seconds, or hertz. Now that you have frequency, we can use the other equation, E equals HF. H is Planck's constant, 6.63 times 10 to the negative 34. And F is the frequency we just found. And when you multiply those, you'll get the energy of the photon, which is 2.18 times 10 to the negative 18th joules. Now you can, if you want to, combine the two equations and solve it all together. That's fine as long as you're showing your work. I like to just do it as two separate equations. It's just how I've always learned to do it. And of course, this is the amount of energy for one photon. And we're going to use that in our next example. So again, we found the energy for the convergence limit is 2.18 times 10 to the negative 18th joules. Typically, we will see energy per mole of photons. So you'll need that in kilojoules per mole. Let's go ahead and convert it to kilojoules first. So there are 1,000 joules and 1 kilojoule. And then we're going to multiply. No, I'm sorry. Let's go ahead and find that first. That'll be easier. 2.18 times 10 to the negative 15th kilojoules. And then we can, from there, multiply by Avogadro's number times 10 to the 23rd, because that will give us the amount per mole. So when you multiply there, you get 1.31 times 10 to the 3rd, and that's kilojoules per mole. So if you had a whole mole of photons, you would need this energy to get to that convergence limit and get the electron to emit from the hydrogen atom. Okay, so let's connect this to some of the properties of metals and nonmetals. Remember, these linking questions can connect to completely different parts of the curriculum. So typically, as you're going across, in general, the ionization energy increases, with a couple exceptions. Remember, at higher ionization energies, it's not going to have that metallic character. It's going to be harder to remove an electron. And then as you go down a group, it's going to decrease in ionization energy as well. So down in this corner, you're going to see the most metallic in character because it has the lowest ionization energies. And over here, you'll have the least metallic in character. Now this makes sense because we typically find our metals on the left-hand side of the periodic table, the alkali metals, alkali earth metals, transition metals in the middle, and then you'll see your non-metals are in this corner over here, which follows that pattern for higher ionization energies, leading to less metallic character. They're much less likely to lose their electron, more likely to gain electrons or share electrons, and behave as nonmetals. Now, this linking question links very further down, much further down in the curriculum, but if you've already been through a prior chemistry course, you might be able to relate here, especially with hydrogen ion concentration. We'll typically use a log scale for ionization energy or hydrogen ion concentration because log scale takes very, very large or very, very small numbers and puts it into a scale that's usable for us. So if you have something, I'm going to use hydrogen ion concentration. If I have something like 1 times 10 to the negative 7, that is an incredibly small number. So 0.1, 2, 3, 4, 5, 6, 7. That is our concentration. We can put that on a log scale, which we call pH, and it's a negative log scale, so that this number is now just 7. And so it is simpler to use. The same thing can be done for ionization energies, like the energy of a single photon for the hydrogen convergence limit had that energy of 2.18 times 10 to the negative 18th joules per photon. Well, if I were to take the negative log of that, that becomes 17.7, which again is a much more understandable number for most people versus this very, very tiny value in the actual form for joules in standard notation. So you're going to see log scales as we get further in the curriculum, especially when we get to acids and bases. But I just wanted to connect it, especially if you're already familiar.